Before we discuss derivatives of inverse trigonometric functions, I'd like to recall to your mind just what an inverse is. So here we have a graph called y equals x squared, or the square graph, and this graph has an inverse. If you remember, even just in everyday definitions, the inverse undoes the thing that you just did, right? So if you step to the left and then step to the right, that's an inverse operation. If you add 4 and subtract 4, that's an inverse operation. It undoes what was just done by the other inverse operation, right? So if we say x squared is 1, then the square root of x is the inverse. It undoes the square function. Now in this example, if I were to ask you what the square root of 4 is, everyone would say 2. Sure enough, 2 is the square root of 4. We all agree on that, there's no question. But why do we not consider negative 2? It's not an answer. If you plug it into your calculator, square root of 4, you only get back 2. What happened to negative 2? Is it not true that negative 2 squared equals 4? How do I not undo that and get back to where I started? And the answer lies in the fact that the parabola is not a horizontal, or does not pass the horizontal line test. It is not a one-to-one function. You see here and here, it fails what we call the horizontal line test, which says that one x value goes with one y value, and then we know that the inverse is a function. Now, that's not the case for the parabola. However, we still can do the inverse. We still have the square root, and we know what the values are from the square root, and it's not negative numbers. The reason for that is we make a domain restriction. The domain, which is chosen from behind, if you will, like it's just assumed to be true. The only way we can get this inverse, square root of x, to be a function so that nobody's confused about what the square root value should be, is to decide what those values should be by convention already. We limit the domain of the parabola to be just this branch on the right-hand side. If the domain is from 0 to infinity, then we can talk about the inverse. So then we know that the range of the inverse, the values we get, will simply always be positive. And that's because those values will come out from 0 to infinity. So that's decided for us. That's chosen. We can think of this in the same way when we talk about inverse trig functions. Trig functions are sinusoidal curves, remember? I'll just sketch a quick one up here. Like here's sine. This thing definitely fails the horizontal line test infinitely many times, and so does cosine. So what we do is restrict the domain on sine and say, you know, we're just going to look at this tiny slice of sine. We decided in trig from negative pi over 2 to pi over 2, just this little bit of the curve, where that's enough that we can get a little representative snapshot, if you will, of the sine curve, but not have any question over what value should come back from the inverse. So what we do, how we define an inverse trig function, is we say we have some value, some angle theta, which is equal to the inverse sine of a number, like the inverse sine of 1. What values of theta make the sine equal to 1? But we do that on a restricted domain from, decided already, negative pi over 2 to positive pi over 2. Just the slice chosen by convention, already chosen for us. We don't have to think about that too much. And we also remember that the inverse sine of t means that the sine of the argument theta, the value of the independent variable, is equal to that t value. So of course we're here in calculus, and we want to find the derivative of this inverse sine function. So how do we do that? We want the derivative with respect to t of the sine inverse of t. Well, we could use this relationship and make an implicit derivative. With implicit differentiation, we can take the derivative with respect to t of the sine of theta equals to the derivative of, with respect to t of t. So that's just sine theta equals t. We know that to be true because we just defined it from inverse sine. And we can take an implicit derivative. The derivative of sine is cosine. The derivative of theta is d theta dt. That's the thing we wanted, right? And it equals the derivative of t, which is 1. So now we have the derivative of theta with respect to t is 1 over the cosine of theta. Or you could call that secant theta. However, we're talking about the derivative of theta, and we have theta in the equation, in the derivative. So that's not very clear. It's not very explicit. We can't leave it like that. So let's attack this sine statement from another angle. What does that mean? If the sine of theta equals t, in terms of triangles, here's a triangle. To right triangle, theta is the angle, and the sine of theta, the sine of that angle, is t. Well, in terms of right triangles, the sine of an angle is the opposite side over the hypotenuse. So I want to turn t into a fraction, so I have an opposite side and the hypotenuse. I can do that without issue if I just put t over 1. So now I know that the opposite side of theta is t, and the hypotenuse is 1. Using the Pythagorean identity that a squared plus b squared equals c squared, for right triangles, I can find the length of this other side. That must be the square root of 1 minus t squared. So I've solved the right triangle. I know all the side lengths. That can help me make the secant of theta, but in terms of t. Cosine was adjacent over hypotenuse, so secant is the hypotenuse over the adjacent. So from this triangle, the hypotenuse side is 1, and the adjacent side is the square root of 1 minus t squared. So finally, I've accomplished my objective. The derivative of theta, if theta is the inverse sine, is 1 over the square root of 1 minus t squared. That derivation for the derivative of inverse sine, which I'll reiterate for you here, the derivative of inverse sine of some argument u is 1 over the square root of 1 minus that argument squared, and then by the chain rule, of course, times the derivative of the argument with respect to the independent variable x. All these inverse trig function derivatives can be found in the manner we just did for inverse sine, so I encourage you to try inverse secant and inverse tangent. I'll post the solutions next week so you can compare your attempts. For us, in Calculus 1, we just simply need to know what the derivatives of the inverse trig functions are and be able to use them as a formula. So you see down here the next question, find the derivative. Y is the inverse cosine of 1 over x. Those are the types of questions we'll do. In Calculus 2, you'll be taking antiderivatives. You'll be looking at these from the other direction and how you have to identify them, and then understanding the relationship between the triangle and the statement really will help you. So if you're moving on to Cal 2, you want to go back to the video, the beginning part, make sure you can do inverse secant and tangent. It really will aid in your understanding. So I'll give you the rest of the derivatives here just straight away. The derivative of inverse secant is 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of u with respect to x. And the inverse tangent has a derivative 1 over 1 plus u squared times the derivative of u with respect to x. So that du dx shows up on every derivative. It's just the chain rule for anything we have inside that's a non-terminal derivative. And then on the insides, like these, they're all fractions. Sine is 1 minus, secant is minus 1, and it has this bonus u outside, and then the tangent is the one that's plus. So that's how we can remember them. I will absolutely expect you to know these first three. You'll need them in Cal 1, and you'll also need them in Cal 2. Now, if you know the first three, it's kind of buy one, get one free. On the right-hand column, these are the cofunctions. Cosine is the cofunction of sine, cosecant the cofunction of secant, and so forth. The cofunction derivatives are simply negative of their buddies in the left column. So the derivative of inverse cosine, 1 over square root 1 minus u squared du dx. The derivative of inverse cosecant is negative. The derivative of inverse secant, 1 over the absolute value of u, square root u squared minus 1. And the derivative of inverse cotangent is negative 1 over 1 plus u squared du dx.